Hi and welcome back. So on the last video we were talking on how you can represent a pure translation. So we saw what is a pure translation and we finished on the topic 2.6.1 and solving the example 2.6. We solved this example which is how you can find the final orientation of referential based on the reference system. And right here we have our translation, pure translation matrix, and right here is the initial orientation. And by multiplying those two matrices, we are left with the final position of the referential that can be which can be a rigid body or another ref system. So the topic 2.6 is about transformations, and we saw that transformations can be a pure translation or a rotation or both of these two transformations at the same time. And now on this video, we will discuss the topic 2.6.2, which is how you can represent a pure rotation around a fixed axis. So let's get started. I will introduce this context, um, drawing the reference systems. So let's draw the ref system XYZ. So we have the axis Z, the axis X, and the axis Y. And we got another ref system which is referenced to this XYZ system. And is our old known A N NOA ref system. That is the basics. Now let me introduce to you the context. Let's suppose that a referential F NOA OA, as you are seeing right here, that I've drawn. And this referential system is localized on the origin of the reference system F X Y Z. Okay, and spinning in an angle around this axis X, this axis So spinning around this axis, spinning around this axis x of the reference system is a vector b. Let me say that again. Not a vector itself, but a point. Let me do it again. Let's say that is a point, and this point is fixed on this reference system. And because of this, we are able to track this point. Let's say that is a point P. So is a point P referenced to this ref system. Okay, and when we decompose this this point on the components of XYZ, we can have his coordinates by decomposing. So if you do this process, you will be able to find the coordinates on the XYZ system of this point. Py, Pz. Okay. As the reference system, as the referential, which is this point, which also can be a rigid body, it turns around the axis x. This point P linked on it will also spin with it. So now I will draw the position of the point after the rotation movement. So this is before the rotation, and now after the pure rotation movement. The point P will appear right here. So we're going to have our point P. And now let me write what I have just said to you as the referential. Spins around the axis x. The point P linked on it will also spin. What that means? That means that the referential um, now is going to change directions. I gonna have to erase this because the ref system F and OA is changed as the pure rotation or or being applied to this point or referential. After the rotation, the rep system FOA changes. But as we are spinning, applying this rotation uh, on the axis X, around the axis X, the the unit vector of this rep system F and O A will not change, just the vector, the unit vectors A and O, and the N will remain as the initial because it's spinning around the axis X. Vector, the point, the point P linked on the rep system. So we will have our coordinates, which are the decomposition of the point on the XYZ coordinate system. There you go. And this is after the rotation movement. After rotation. And as you can see, is around the axis X. Now, if you look on the direction of the X axis, if you are looking at this view, the axis X will not change, and we will see only the axis YZ. So let's draw the axis YZ. Z, Y, and the vectors after the rotation movement. So as we are looking on the front, um, we will only see the axis YZ. And remember, uh, is on the top of the axis X, and the unit vector, and it doesn't have any change because the rotation is above this axis. So as this point P is moving, we will have the decomposed components of O and A for this point P. So let me illustrate this. On the axis Y, the point P, it starts right here. Let's say right here. And after the rotation, this point P will be right here. So let's say that's the final position on the X for the axis Y, and that is the initial position for this axis Y. So let me pass a dashed line. From here till here, we have the final position. Which we call L1. We have L2, and PY. For PZ is the same concept, uh, is the decomposition of the coordinates of the point P to in components, sorry, x, y, and z as this point are doing the rotation movement. Okay, so we how we can determine the components px, py, and pz. Let me copy this and paste right here. So, as I said, this rotation, this transformation of pure rotation is occurring on the axis x. So the axis x, it will not have any change. It will be Pn, which is the vector n of the reference system Fnoi A. Let me show to you right here. Okay, the unit vector n is pointing on the same direction as the axis x, so it doesn't have any change. So it's going to be Pn and Py is equal L1 minus L2, which is equal right here. L1 is the value of the point PO decomposed on the axis Y. So right here we have this angle, so we have to multiply by the cosine of this angle, minus, because we are doing the difference of L1 and L2 to find Py. Okay, so it's going to be Pa sine of theta y, because it is the decomposition of the point on the axis of reference A, and Pz is the point sine of theta plus Pa cosine of theta. We just have to substitute these angles on these equations, and we are able to find all the localization of the point after the pure rotation movement. And also we can represent this in a matrix form. So Px, Py, and Pz. As we wanted to find them, we need to multiply by the matrix of rotation. So that is the matrix of rotation that we are applying on our point P. And this is the referential system that we are using to track this point. And we can write that the final position of the point P XYZ is equal to the rotation on the axis X with some respective angle multiplied by the old position referenced to the reference system and OA.